So, welcome to the second of this year's technical lectures by David Jerison. Continue talking about double sets of geometry, double sets of solutions to semilinear equations.
All right, thanks, Carlos. So I'm going to remind you what we did last time. And I mentioned the Ricci flow, which is the derivative of a metric is equal to minus twice the Ricci tensor of the same metric. That's the definition of the flow. And we'll imagine that this is happening on a manifold cross. We'll start at a negative time and end at time zero, maybe open-ended time zero today, just in order to explain visually what it is that we were talking about last time. So last time I drew a picture, and I'm just going to draw that picture upside down, the same picture, which is that if you're flowing into a singularity, then there are these interesting rays that come out of the singularity. So we're thinking of time as starting here at minus t and ending at zero, and we're going to some singularity. And the idea of much of the work on Ricci flow is to understand what happens at these singularities. And the cases of interest are the sort of are some models which are usually called solitons. Okay, and the solitons are the same as what are known as ancient solutions, which means that minus t it goes all the way to minus infinity. Ancient means that the solution existed for all time and just ended in this catastrophe at the little green dot here. And so those are the solitons, and they're very rigid. It's exactly the same. Well, sorry, it's analogous to Liouville theorems in elliptic equations. So the fact that you have something which is defined on a very, very large, complete set means that space means that it acquires some tremendous rigidity, and you can characterize those solutions. And then the game is to show that the ones which only exist locally resemble the one which is the model case, the soliton. And so that was what was accomplished brilliantly by Hamilton and Perelman. Hamilton did the case of spheres, S3, which is contracting to a point. And what Perelman did was he managed to also do, so those are called shrinkers, and Perelman managed to do the case of S2 cross R, shrinking to a line. Okay, and that's a neck pinch. Right, so this is a neck pinch, which is exactly what does the surgery in topology. Okay, so that was the story of this subject, and mediating this was this gadget which I called G tilde last time, which was a metric on space-time, which is constructed from the original metric. So it's defined on this space here, right? Now, it's a little weird because it's a degenerate metric. It has a lot of complexity. And actually, a very large fraction of the complexity of the situation for Ricci flow disappears when you do the elliptic case. Because instead of the metric being degenerate, our metric is going to be non-degenerate. So there's no problem defining the geodesics, which there is when the metric is degenerate. So there are all kinds of technicalities. Also, the existence theory is quite difficult for mean curvature flow and for Ricci flow. But for elliptic equations, we already have the solution. So there's nothing to be done in that respect. We also actually know what the singularities look like, because we can expand spherical harmonics at singularities of harmonic functions. So there's just nothing going on. It's all about the interaction of the level surfaces. Okay, so I want to remind you of the two clues that I mentioned last time as to why there should be such a geometry. Just to remind you and fix ideas, this is not. So the situation was that you had a non-zero, we're in the sort of non-degenerate case here, okay? And I defined the, so we're thinking of the level sets. These are things that I call M tau, which is the set where M is, so this could be either locally or there could be some ambient situation, okay? We defined a vector W, which was grad U divided by grad U squared, okay? And that is really, in disguise, the vector d by d tau. All right, that's the parameter tau is the parameter of the level set, and it's the directional derivative, but scaled according to u. Okay, that's why there's a u squared in the denominator and u in the numerator. This is what we mentioned last time. Okay, and it's pointing in the normal direction because grad u is pointing in the normal direction. Okay, so the amazing thing was that there was another player in the story, which was the Hodge star of du, which is also extremely canonical. Hodge star depends on the metric. It depends on the ambient metric. And this is the thing which is actually the same when restricted to the level surface as the length of the gradient times the surface area of the surface. And this has a name, it's called flux. All right? So the remark, which was due to Calderón, is that the Lie derivative with respect to W of star du is equal to 0, right? And this is telling us that there are interesting differential equations associated with this flow, which are not just about single level surfaces, they're about families of level surfaces, right? And that's the okay. So now I'm going to tell you what the conjectures that I have in this subject are. I have to warn you, there are no theorems, all right? There's just guesses as to what's correct here. And I have pieces of the story, not the whole story, all right? This is a work in progress, and I feel like it's very close because I can tell you some things, but nothing is, barely anything is proved. I'll say a few things that are proved. And so here, let me tell you what the conjectures are, okay? So it's just really going to be one conjecture, and then I'll make some other, I'll have some applications next too, all right? So if Laplacian of u is equal to 0, and the gradient of u is not 0, I think I can fit this all in one box here. So 5 is enough. So there is this magic metric g tilde, which is some function of grad u, grad squared u, grad cubed u, right? And in the general Riemannian ambient case, it should be the same thing, but these gradients are the covariant derivatives with respect to the metric, right? And of course, it will depend on the metric as well. But my background metric is just Gij is equal to dx j squared, the sum of, sorry, g is equal to dx j squared. Just the standard metric.
So David, sorry, please. When you write gradient u non-zero, it means it's not identically 0.
No, it means
or never vanishes.
It never vanishes.
Right.
It never vanishes.
Okay, so
I'm
no
just in a neighborhood where I'm just studying a neighborhood where it doesn't vanish. I'm just taking a patch.
Got it.
And it's just a purely local statement for now. There will be some global stuff, but right now this is the assumption. So this is on some open set.
Got it. Yeah. Okay.
Thank you for making that mention. Okay. So there is this thing such that. So the first property, which, because I'm telling you this in advance, you don't know exactly what it means. The curvature tensor, the whole Riemann curvature tensor of this thing is identically 0 for the solitons. Okay, I'm going to tell you what the solitons are next, almost immediately. In particular, they include every quadric surface. Okay? So the point is that this is universal in the sense that it's all quadrics. And that's incidentally why you need third derivatives, because otherwise you wouldn't possibly be characterizing this stuff. So, Riemannian geometry involves sort of curvatures, second order things. But here, the flat things are the quadrics. And that's what I'm saying. Quadrics are flat. All right? The second property is that the Laplacian of the log of the volume element, the Radon-Nikodym derivative of the volume element with respect to its standard area volume measure is non-negative. Okay? So notice this depends on 5 derivatives of u, right? Because g depends on 3, and so the volume element depends on 3, and then we're taking another 2 derivatives. All right. So this is part of the reason why I haven't worked this out yet. It's because these computations are very long.
What is V tilde?
The third,
Excuse me, notations. I don't. V tilde. What is it?
so let's see. I couldn't hear your question.
What's V tilde? What is V tilde?
Who is
He's asking what's V tilde.
dv tilde
V tilde.
is the square root of the determinant of g tilde with respect to any coordinate system times d. Let's just say coordinate x one much. In standard coordinates, it would be this. Okay, so this is by definition the volume element of a Riemannian structure. We're going to see in a little bit that this is a very fishy object when we actually construct this thing, but I will explain that. Okay, but anyway, this is the case. All right, so this is completely standard. This is what the volume element of a Riemannian or a semi-Riemannian is. We're going to discover this is, and it's worse than that. We'll be there in a few minutes. Okay. So the third property is that the one which is supposed to echo. Oh God, I didn't even say it. So what was the punchline here from last time? The punchline from last time was that there was this amazing formula, which was way up there at the 6th derivatives. So what was it? It was the formula that dt minus the tilde Laplacian of the curvature tensor associated to this one was some quadratic function of the curvature tensor, the same curvature tensor. Okay, this is the miracle formula of Hamilton, which was later interpreted by Chow and Chu and then used to great effect by Perelman. But already it was being used by Hamilton. It's just that it was really souped up in the work of Perelman. Okay, so this is the identity, all right, the magic identity. And this is some very specific natural quadratic form which you can work out. Nolan Wallach observed that this is related to some ideas in Lie algebras. It depends on the metric in disguise. Okay, it's a beautiful natural thing, but we don't have time to describe exactly what it is. Anyway, this is the corresponding identity is what I'm conjecturing. And it's exactly the same thing. So notice that this depends on 7th groups. All right? It's exactly analogous. Once you get to the level of G, you're stuck with this being the complexity of the setup. All right. So those are the ideas. And now I want to mention potential applications. Now, I'm going to talk about them in the third lecture. Okay, and I also, this was supposed to all be in the first lecture, and everything is getting squeezed, and I'm not sure exactly how far I'm going to get. But in any case, I certainly can't. But in order to tell you where this is headed, I will at least give you some indication of what's going on here. So the first problem is an isoparametric problem for capacity. For electrostatic capacity. Right? Now, this is a very famous, maybe 60-year-old conjecture of Pouillet and Say. Right? And what it says is that the convex body of least capacity, electrostatic capacity, with fixed surface area, is the flat disk. Okay, in three dimensions. All right, so I'll describe that, and the point is that it's exactly in this quadric surface framework, and so it will be obvious when I describe the geometry to you why this problem should be amenable to these tools. Okay, so the second problem, it's a little less obvious. Well, it should also be obvious, but only to people who actually know exactly what the proof is. There's something called the Bayes conjecture. And unfortunately, I didn't do my homework and find out what the other name for it was in the former Soviet Union. I'm pretty sure that it's not unique to Bayes, this conjecture, but it's also a very old conjecture. And what it says is that if you have a harmonic function in the upper half plane, and its gradient is equal to 0 on a subset of n-1 positive measure of the boundary of the plane xn equals 0, then, so if this is true, then gradient of u is identical. All right, so there are only constant functions have this problem. Now, this conjecture is false, okay? And it was disproved by Tom Wolfe in a very famous counterexample. Very, very subtle, beautiful counterexample. It's just phenomenal. But Tom believed, and I believe, that the minute the function is smooth up to the boundary, it's true. Okay, his example is only C1 epsilon for some epsilon. It doesn't even have two derivatives. So the technique should have to do with curvature, if the thing is going to be true with this further smoothness assumption. And indeed, this second property will just kill it. This is the end. If this is true, it's going to win. Okay? This is all that's going on if you know how these things are proved in two dimensions. Okay, so that's conjecture number 2. So number 3, or application number 2, provided all this other stuff is true and it works out the way it's supposed to. Okay, so number 3 is, in terms of applications, is the following problem. Suppose you have a solution to this semilinear equation, all right? Suppose you have a solution to this. Then one of the things that you'd like to be able to do is to prove Liouville-type theorems. And what are Liouville-type theorems? They say that if you have an entire solution, so this is on all of R n, you want to be able to know what all the possible solutions are. But of course, that's useless. There are too many. It's not necessary to say that. A lot of the work, as I mentioned last time, in this subject has to do with concluding that the function is one-dimensional. It's just a function of one variable in one direction, which means that the level surfaces are planes. Okay, but there are other cases which one can understand. Okay, and one of the interesting ones is the assumption that the set where U is positive is a contractor. Okay, so a topological constraint on the level, the super level set in this case. All right? So the question is to characterize these guys. All right, and there's an actual result in 2 dimensions, which is due to me and my former student Nicola Calderón. And what it says is that in a case where f of u is the simplest possible thing, which is it's the delta function of u. This is the scale invariant case, or scale covariant case, and it's the case of free boundary problems. It's one of the most interesting cases. The second interesting case happens to be delta of 1 of u minus delta of minus 1 of u, which when you blow it down is the case of minimal surfaces. All right, so these are incredibly closely linked. And this one here, there's an answer, and the answer is interesting because you can exactly, there's a rigidity, there's a dilation family, and so on. Anyway, I'll be describing that next time. So that's the 2-dimensional case. Now, what all 3 of these conjectures or possible potential applications share in terms of their features is the following. There are known, good, interesting theorems in 2D, already known, and this should provide a new proof of every one of them, which can be extended to 3 dimensions and maybe to higher dimensions. That's the point. Okay? So the number 1, the one about capacity, the corresponding conjecture is about ellipses, and it collapses to a needle, to a segment. And we'll be describing that geometry in a minute or two. And the Bayes conjecture in 2D is the subharmonicity of analytic the logarithm of an analytic function. The property that the logarithm of the absolute value is harmonic. And the third one, as I just said that we have a 2D result here. This is the result that I would like to mimic in higher dimensions, and there are plausible candidates for what that could possibly be. And obviously, the finitely connected case is not even solved in 2D, and the infinitely connected case is probably very challenging and extremely interesting, and if we have time, I will discuss that as well. It's directly related to the Shirk surface in minimal surface theory. Okay, so all of these things are connected, and they're directly connected with geometry. That's the message.
So on property A of the conjecture, you mean it's identically 0 only for the solid, for the solitons, right?
Only.
If and only if.
Only, yeah, if and only.
So when n equals 2, what is G tilde?
Pardon me?
When n equals 2, on a disk, do you know what G tilde is?
Yes. So I know what G tilde is in n equals 2, and we may even get to it by the end of today. We will certainly get to it tomorrow if we don't get to it today. That's, yes, okay? That's what I have. And I also have all of the tools to get to the n-dimensional case, except that there's this problem in algebraic geometry. If I were a better algebraic geometer, I think I would also know how to do the n-dimensional case.
And what are the solitons? They are the quadratic?
You're going to say that in just a second. It's not just the quadrics. That's exactly what we're doing next, is we're going to say what are the solitons, which I would have done much sooner. I thought I was going to get to that also in the first talk, but you're getting to it now. Right now, we're going to tell you what the solitons are. Okay, so because of the motivation, so there was also a potential application last time, which had to do with level sets of eigenfunctions. And you notice that the level sets were ellipses or ellipsoids. So obviously we're interested in quadric surfaces when we do this. So it turns out that when is a level surface of this equal to a quadric? Okay, when does that happen? Well, the answer is that this is known, and it goes back. The first instance in which this was thought about was by Isaac Newton. Okay, so Isaac Newton invented the mathematics behind gravity as we know. And the gravitational potential, which is the potential energy of something, is a harmonic function. All right? And the problem that Newton solved or observed was the following. He took an ellipsoid, honest to God, an ellipsoid, and then a concentric ellipsoid. Okay? And he imagined that there was a shell of mass. And he was interested in how much that gravitational field would affect what was inside the Earth. Okay? So the question is, what do you feel if you're a particle inside here? Okay? And there's this shell around it. And the reason why he was interested in ellipsoids was that he knew that the Earth was not completely round. It was closer to an ellipsoid. They knew it had a bulge. Okay? It's more like an oblate spheroid. And so he was asking that question, but it's even for the sphere, concentric spheres, it's an issue. You know, how do you know that if you're over here, it's not going to sort of pull you in one direction or the other? What's going on? Now, this is, of course, not the Earth. The Earth has different densities, right, inside of it. So just don't think of it as being like if you're with Jules Verne and you're journeying to the center of the Earth. This is not what's actually going to happen. But in any case, the answer is that the field here is zero. Okay, the potential is constant inside. This is what Newton proved. All right, and it was so. This was probably in 1660 sometime, and then Ivory, in around 1800, figured out what the field was outside. Okay, what the gravitational field is outside of the Earth. So this is relevant for the solid Earth. It's relevant for anything. Okay, and the answer is that the level sets of the potential energy, the gravitational potential energy outside either of this one or the one which is filled up, it doesn't matter how much of it you put in, are what are known as confocal quadrants. Sorry, I'm going to put it up here. Confocal quadrants. Okay, so this is a classical subject, and everybody knew about it in the early 1800s, and you've probably forgotten, all of you, what it is. So, you know, I have to explain, all right? So in order to explain this, I'm going to start with the two-dimensional case because it's much more easy, much more accessible. So in 2D, you can just organize them and see how I presented this. I think I threw it to this page. Yeah. The way that you can use complex analysis to write down what you're doing. So you have x plus iy now, which is the two rectangular coordinates. And now we're going to write down the formula that it's cosine theta plus it. Okay? This is going to be our coordinate system. And now I'm going to show you what the geometry looks like in the two-dimensional case. And it's very easy to see what it is. So first of all, let's think of t being constant. Okay, we fix this parameter here. Okay, so that's going to be a harmonic function because of conformal mapping theory, right? Both t and theta are harmonic functions. Okay, so what are the level sets of t? That is t equals constant, so that's one possibility. The answer is they are these confocal ellipses. I'll draw the picture in a second. Okay, and theta equals constant are confocal hyperbolas. All right, so let me draw the picture, and then I'll be able to fill in what's going on. So here's the ellipse. So what happens here when t is constant? Just take the case t equals 0. All right. When t is equal to 0, it's the range of cosine of theta, which is between -1 and 1 on the real axis. Right. This is the collapsed. Right. And then all of the others have the same foci. So the foci are plus or minus 1. Okay, so first we have the foci of the all of the they're not concentric. They have the same focus. So when we go out to infinity, it's very important to realize the thing is getting rounder and rounder because from the view from infinity, plus or minus 1 are practically the same point. Right? So they're definitely not concentric ellipses. And then the hyperbolas are perpendicular. This is an orthogonal. That's because of conformality. This is an orthogonal family. All right. So you could argue that these are my solitons, and I think that they're good for quite a bit. But this is not the full story. The correct story is to also consider the level sets of linear combinations of these guys. All right? In which case, you're getting these things in between, which are spiraling around. All right? So let me remind you of the simplest degenerate case. The simplest degenerate case, which is very obvious, and then it will become easier to digest this particular thing, is the case where you squash the two, you look from infinity, if you like, or you degenerate so that -1 and +1 go together. And that has a name that's called polar coordinates, right? So that cosine is really the same as the hyperbolic cosine, and if you do the merge, you'll get the exponential. And so what you get is x plus iy is equal to e to the, well, now I'm going to reverse the roles of the variable. Well, maybe I'll call this s plus I theta. Maybe I'll do it this way, right? So of course the radius is e to the s, and the picture is you have these rays going out. That's where the hyperbolas went, right? When the hyperbola comes here, it gets very, very straight. And if you think of the hyperbola at infinity, it's going out on a straight line. So these things and so on. And so what these other curves are is they're Bernoulli spirals. Those are the other secret curves in this subject. All right? And you have to deal with all of them, and that's what makes this so complicated. If it were just the quadrics, then I already have all the formulas. But that's not correct. That's not what gives you the correct GL2, GL3 invariance to make this a subject for which it's fair to write this expression here, for instance. Have it make sense and be a natural geometric thing. Okay, so that's the situation. By the way, if you take one of the foci and you send it to infinity, then the level sets are parabolas. And they're confocal parabolas, and it's just all the confocal parabolas rotating around. Those are the lines. So the simplest possible model for this thing is you take one point in the center, and you take all the parabolas which have that focus, and those are the lines. Okay, so this is the 2D picture, and I'm going to have to introduce some complexity here. Which I will do after I've explained to you how this works in 3D. Okay, so now we're going to do 3D and explain what the solitons are in 3D. So again, this is extremely old. It certainly goes back to Ivory, so 1800. But the full story was not understood until Jacobi in the 1830s. So in 3D and in higher dimensions, this also works in higher dimensions, so sorry, I'll probably write it. So here's what I want to write down. AJ mu minus aj. This is the one I want to write. And then with malice aforethought, I'm going to set that equal to minus 1. I'm not sure. Well, so sorry. Let's just have this be a function of x and mu, and then the surfaces, the quadric surfaces, are going to be, these are the quadric surfaces. Now, this is all quadric surfaces if you move the parameter mu. All right? And to describe it in a little bit more detail, I'm just going to do this in the 3D case just to have a specific picture. Yeah, I think I'm going to draw this a little bit lower in order to have room to squeeze something else in there. So here, can you all see this? So here's let's put A1 here, A2 here, and A3. Right? Okay, so what's happening is that you can stick a parameter mu1 starting at minus infinity. And when you do that, what's happening up here with this equation is that you're getting all the ellipsoids, because the signature is plus, plus, plus. The way my convention is, all of these denominators are negative in this case, and so there's a minus 1 on the other side, so I get the signature is plus, plus, plus here for the quadrants. And then the next one, mu2, which is in here, is minus, plus, plus. These are one-sheeted hyperbolas. And the next one is the two-sheeted hyperbolas, minus and plus, plus. Okay? So these are all the quadrics, and we don't need this other range. We've already got all the quadrics. Okay, so this is the picture, and these are the confocal points. All right, this is the algebraic formula for the confocal points, the family. So all on here, and then this beautiful what ellipsoidal coordinates are is the correspondence between x1 squared, this collection of coordinates, and this other collection of coordinates. Okay? These are called ellipsoidal coordinates, and of course they coordinatize an octant of this thing. So it's not a perfect coordinate system. It's fine. Also, there are some degeneracies if A1 is equal to A2. There's all kinds of things where this is only the generic case. Okay, so now I want to describe to you, so the miracle which Ivory observed and then Jacobi actually got the computations correct, is that if you solve the equation phi prime of mu is equal to q of mu to the minus 1/2. So this is a differential equation, where q of mu is the product of the denominators, mu minus aj. J equals 1 to n. So it's a degree n polynomial. So the observation is that solutions to this equation, so now if you let uj be equal to capital phi of mu j, this function is harmonic. Right? This is a separation of variables. So people don't know this, but separation of variables, which was for spherical harmonics and all these wonderful things with a sphere, there's a completely analogous setup for ellipsoidal coordinates. And almost every property is inherited by that situation, including the fact that, for example, if you have a polynomial on the boundary, it's the harmonic extension of it is a polynomial. That works for ellipsoids, not just for spheres. So this is an extremely beautiful thing, and the issue here that people had, and the reason why you can't say that Ivory really solved the problem, is that people didn't understand how to compute the integrals of these things. These are called elliptic integrals, and the mechanism for computing them was discovered by Jacobi about a generation later. So what he realized is that you could apply this abelian integral setup and solve for these things. And what he really did, which I probably won't have time for, is that he was actually able to solve them so well numerically that his formulas are still used now to solve these things. This is way better than anything else. They're super convergent series because they're square exponential fast. Anyway, what happened next is various developments by Riemann and Weierstrass, and the simplest way of describing what's happening here in the 3D case is that when you solve for these things, these functions u, what you're actually constructing is a conformal map from the upper half plane to the rectangle. Okay, and the mu1 corresponds to a u1, which is along this distance, and this is called the quarter period of the Weierstrass P function. And here's u2, and here's u3, and this is where they go. And the reason is that this is what's called a Schwarz-Christoffel integral, and there's when you do it, the integral, you get a right angle turn here. You get a right angle turn here, you get a right angle turn here. And then the last one is the right angle turn at infinity, and it comes back on the other side. So this is the map, this coordinatization. Just one solution to this evaluated on the upper half plane maps to this rectangle. Okay? And the whole theory of So essentially, uj is equal to the Weierstrass P function of uj. This is the correct point of view is to write things in terms of the inverse function, because in this direction it's a multi-valued function, whereas in this direction it's a single-valued meromorphic function on the whole plane with double periodicity. It's a fabulous construction. All right? So this is the Weierstrass P function, and this is where it goes. Now, this statement is only true if the sum of if A1 plus A2 plus A3 is equal to 0. Of course, there has to be a convention, and there has to be something going on here. So every damn thing in special function theory has a convention, and people do different conventions. So this is a hopelessly unpleasant issue that you can never be sure that you have a statement that's correct in this subject before you check everybody's notation. But anyway, this is All right. So this is one of the pictures. Okay. So now I'm going to tell you something else that's subtle about this, which is actually very serious. And this is where we're going to start to think about algebraic geometry. It looks like this is a problem in real analysis, but it's not. This U2 is purely imaginary, and this U3 is somewhere else in the complex plane. And so the right way of thinking about this problem turns out to be not at all to require that all the numbers are real numbers. I want x1 through xn to be complex numbers, all right? And I want to do things which are purely algebraic to these things, which has the effect. So let me go back to this thing that was there where I was telling you about this formula here. So notice, here's a complex number of which I have to take the square root. Okay? So that's actually already somewhat unpleasant. And it turns out that also the signatures of all of the tensors are scrambled, and there are factors of I everywhere that you have to organize correctly, which I can explain how to do this, and I will in a second. But the point here is that when you take the log, the argument doesn't matter. The argument turns out to be constant, and so this equation still makes sense. Okay, so it's it's very, the signatures of these things don't necessarily have signature like a Riemannian metric. They can be not even semi-Riemannian, but also have factors of I. So anyway, that's the wording. So now I'm going to show you, in the case of two dimensions, how this works. All right. So that you'll feel comfortable that it's going to be possible to do this in higher dimensions. Okay. And I'll explain pretty extensively what's going on. Okay. So here's the first observation, which is just a trivial consequence of this formula here. So this formula is a formula for the change of variables, right? And so that means that we can write down the metric dx squared plus dy squared, which is the one that we started with, right? It's fundamental because the Laplacian is expressed in terms of that metric. So this is the only object of study besides this one scalar function, which has this. That's all we're doing. Okay? So what is it equal to? Well, this is a well-known fact. You take the derivative of that cosine, and you get a sine. Okay, and this is what you get. All right. So I apologize. There might be a quarter or something. I mean, I'm totally ignoring constants here. Maybe there's a quarter. I don't know. Maybe not. Okay. In other formulas, there's definitely a quarter, which I'm going to skip. So I'm going to rewrite this in a very important way. U1 is theta, but now U2 is going to be IT. Okay? Because really the covering space that we're talking about here is a cylinder, and it's in complex space. All right? So that means that the solution is written as U1 plus U2 times sine of U1 minus U2. Okay? So this expression here got rewritten in a trivial way because this is just the conjugate, right? So this is correct. This is what it is. This is what this factor is. Okay, when restricted to the appropriate real values. But now the metric has changed. It's du1 squared minus du2 squared. Okay? Now, so this is a more general formula, and it applies to complex U1 and U2 and complex x and y. It's an algebraic expression that's this way. So this is the way I want to extend this real thing to C2 cross C cross S. All right? And the point here is that this guy is symmetric in U1 and U2. If I permute U1 and U2, it's just the same object. So this has an S2 symmetry, which is very important for this subject, because eventually what we're going to want is GL2 symmetry in the variables U1 and U2, or covariance with respect to GL2. So there's a second formula for this guy, and it's the following. It's sine squared U1 minus sine squared U2 times du1 squared minus du2 squared. Okay? Those are just the same thing by a trig identity. Okay, so this is the setup, and now you can, if you want to calculate on the model case, you work directly with this, in the coordinate system U1, U2. Right? And you figure out what's going on. So now I'm going to tell you what it is over in 3D. All right? I'm going to tell you what the formulas are. And that's just for what I've just done over on that other block. So maybe I'll raise this. It's clearly not going to get to formulas. So what are the formulas here? So I claim that dx1 squared plus dx2 squared plus dx3 squared, by analogy with what I did over there, this is up to a constant which I think is a quarter, but I don't remember. Oh, yeah, I'll write it this way. It's this, where Pj is equal to the Weierstrass P function of Uj. All right? So it's this expression, and then I just permute the indices. Right? So this formula is analogous to this one. Okay? So what is the formula that's analogous to this other one? Well, so the answer is that you want to think probably about both of them. And they're sort of equally important. And this one is better in the sense that it's telling, it's a single product. It's not a, okay? It's just a product of things, whereas this has differences of things in it, all right? So the second formula, I haven't told you this yet, but the rest of the history of the subject is that the way that Jacobi computed these functions, the Weierstrass invented the P function 40 years after Jacobi. So essentially, Jacobi already knew about these functions. He just didn't write it exactly in this notation. And what he did is he wrote things in terms of what are called theta functions. And the theta function formula for this guy is the following. It's theta of u1 plus u2, theta of u1 plus u3, theta of u1 minus u2, theta of u1 minus u3, divided by theta of u1 to the fourth power, theta of u2 squared, theta of u3 squared. This is the factor on du1 squared. Okay, and then it's symmetrical. Now, these guys, these theta functions, this is for the theta function which has the property that theta of 0 is equal to 0 and is compatible with this particular P function. So these are the ones which are computable by incredibly fast algorithms, and these are the ones that Jacobi invented. And it's literally just, for analysts, it's literally just the solution to the heat equation extended to the complex numbers, on the heat equation on the circle. Now, in higher dimensions, there's something called the Riemann theta function, which has to do with a lattice in higher dimensions. And there's an object in algebraic geometry called the Jacobian, which this is associated with. And the point is that these things are meromorphic symmetric two tensors on the elliptic curve. So literally on the triple product of the elliptic curve modulo S3. And these are the standard objects considered by algebraic geometers. So this is a natural gadget in algebraic geometry, and we're trying to do some algebra with it. Okay, so everything that I will construct in differential geometry is expressible algebraically. And as a result, the constructions, which depend on the Levi-Civita idea, you know, in the distance, are going to be good. So I think I'm unfortunately out of time. I will give the formulas for these things next time. It's incredibly long. I just have to warn you about one thing. So why is it that I can't do it quite yet in 3D? So I already understood this pretty much 3 years ago, but on a much more, somewhat more superficial level than now, but I understood it at least in the ellipsoidal coordinates, in the Euclidean coordinates. And I thought, oh gee, all it depends on is the Taylor expansion to order 3 of U. So therefore, you know, by some algebraic version of undetermined coefficients, I should be able to guess what this thing is. So I asked my good friend and colleague, Jack Lee, to program this in Mathematica. And the question came back with 44,000 terms in 3D. 44,000 terms. So you cannot do this by just guessing, oh, it's going to be some formula of this type. You have to use something much smarter. And I already actually even knew what some of the smarter things were, but this will lead to it a little bit better.
So, but this was an exact formula? With the 44,000 terms?
No, the 44,000 terms is what you're trying to do is you're trying to take the harmonic function C1U1 plus C2U2 plus C3U3, and it's this explicit thing here from these things, and then you're asking yourself, how are you going to make G tilde produce du1 squared plus du2 squared plus du3 squared? How are you going to devise this formula F, which depends on grad U, grad squared U, grad Q? How are you going to cook up a formula which does this? Okay, that's the one which, of course, is constant, right? The curvature. This is a flat metric. The curvature of this is identically 0. So it's fulfilling part A of this scheme. It's the one that you want. Okay, so I can do it individually. If C2 and C3 are 0, or if one of the others of these is 0 and the other one is non-zero, I know how to do that. And I think that that's relevant to problem 1, and there are other problems which it's relevant to, like the one I mentioned last time, one about convex level sets. But so let me just make one more comment here, which is all these level curves. It looks like, God, just what a mess, all the spirals and stuff like that. But there is a distinction between the ellipses are the only compact ones. The hyperbolas or the quadrics are the only complete ones. And the rest are not complete. And so even though they have the differential equation, the local property, that they're sort of nice, they're flat, they don't have the global property because they're not complete. So when you do theorems in differential geometry, especially in the non-compact case, it's incredibly important that the manifolds you work on are complete. Otherwise, many theorems, many methods just don't work, which is a good thing. You don't want it to work for all of these guys. On the other hand, as I say, the trajectories are what I'm interested in. They are not those other surfaces necessarily. All right, so are there other questions? I guess
I was going to ask it again. What were those 44,000 terms?
What were the 44,000 terms?
In other words, was that a calculation that gave up, or a calculation that was giving something exact?
That was the following thing. So I had a guess for what this should be, okay? But there were some undetermined coefficients in it. So it was an algebra question, which is, if you allowed for, and these things were undetermined, although actually I think we eliminated, just did 2 because I already know how to do it with 1. So if you just do it with 2. So you have 2 of these coefficients, and then those are undetermined, but you want to somehow eliminate them in the end and get to this, okay? And you have this formula here, except it was, in my case, it was with mu's. It was with this. Okay? And when you do that, there's a change of variables between d mu. So this is part of the problem. There's a change of variables between these two things here, which meant that there were also square roots in the problem. So the advantage of this coordinate scheme is that you've taken the correct branch of all the square roots and all the factors of I. So the Mathematica couldn't tell the difference between, so it had to treat them all as separate. And there are a lot of, okay? Whereas, as I say, this is purely algebraic. I'll have to explain that next time. But, so there are a bunch of things which get squared, and then other things where you know which branch it is, and so it should be a lot less than 44,000 terms. seriously, I think that some algebraic geometer will just look at this and say, oh, this is the blah, blah, blah. And it follows from, maybe not. But, we'll see.
Thank you very much. Any further questions? We wait till tomorrow.
Yeah, so I'm not sure how many of these applications I'm going to get to. I have a long spiel about it.